All right, recording is rolling. Welcome to Monday, September 26th. So today I'm going to take all day to just do a bunch of textbook problems with you guys. So I'll start with the start one side at a time with you guys, and then maybe change some of the numbers, but otherwise I'll follow with you. Okay, and then if we have time left over, then I'll just pick some of the other ones, and then I'll do as many as we can. So guys get lots of practice. Later this week, what I'd like to do with you guys anyway is do a bunch of lab activities. Freshman lab, very non-frame, spring concept activity. If I can fit in a Kahoot sometime with you guys with some simple questions, I'd like to do that too. Of course, we're all keeping an eye on this hurricane. We're gonna be at school 5 days this week, so time will tell. As of right now, looks like we're probably gonna be here all 5 days. So who knows? Oh yeah.
For this homework, what are the questions that we're supposed to do? Do all of them?
No, not all of them. So yeah, send you guys here. Okay, so there's chapter 4, forces in 1 dimension, and then chapter 5, forces in 2 dimensions. Okay, so chapter 4, forces in 1 dimension. It's the same 5 that I went over in class with you guys. So number 58, number 60, and 64, which are high net here in the middle. Number 69, and then number 92, which is this classic double elevator outward. First, if you want more practice, solve some other fun problems there too. And then one we're going to hit today, it's got these star 2, so the ones that I signed. We did it. Oh, I forgot it typed up here too. So here we go. Number 56, which is high up here in the top right. Number 83, number 90, 91, and 97. There you go. All right, so I signed to you guys. Physics honors. All right. Okay, good. All right, so and once I assigned you guys, go ahead and go over with you guys right now. And so number actually start with 83, which is down here. Number 83. You walk so many meters south and so many meters east. Find the magnitude and direction of the resultant displacement, both geographically and algebraically, which really sounds like past material. Actually, this sort of is a past material question. Now, how this could apply to what we're doing now is, well, vectors, right? So it'd be like force vectors instead of displacement vectors, but really similar idea. So say we're starting some location, and we're going to go many so many meters south, followed by so many meters east. I'm going to change the numbers just on my paper. Like that. Right, so many meters south, so many meters east. Okay. Now, but before I start writing any magnitudes on here, see how this is going to like why is this question in the 2D, like forces in 2 dimensions question, and why did I sign this, right? Because you could do a very similar setup for forces. Suppose I have an object here. I put a downward force and a sideways force at the same time. Isn't this going to kind of move down to the right? Right. In fact, if I push really hard down into the side just a little bit, it's going to move down a lot more than it moves to the right. Right? If there's no other forces, like if you get rid of friction and everything, then it will accelerate. So a net force will cause acceleration. So I'm going to say 80 meters south and 60 meters east, okay, just for the notes. And you guys have your homework numbers. I'm giving you guys some notes numbers, but it's the same premise, right? Okay. Notice how I've connected these vectors tip to tail. You could also do that with force vectors. You could solve it geometrically by connecting vectors tip to tail, right? We've done that before. So this is kind of a good review question right here. Basically, if you go from the tail of the first vector to the tip of the last vector, what's this vector called? Starts with an R. Resultant vector, right? That tells you the net effect. In this case, it's a displacement, but you could tell you net force if those was like 80 newtons and 60 newtons, right? Now, who could tell me what my net or my displacement is? Or how would I figure it out? Could be the square root of 80 meters squared plus 60 meters squared. Hey, that's Pythagorean theorem, right? You guys see that's where that comes from, right? Square root of a squared plus b squared is Pythagorean theorem. Okay. Shouldn't that work out like 100 meters? Right. How did you do that without pulling out a calculator? Yeah.
It's a 3, 4, 5 triangle.
Boom. 3, 4, 5 triangle. See how the proportion 60, 80 to 100? That's a 3, 4, 5 proportion. Is that okay? Now you guys don't have a 3, 4, 5. I think you guys have a 45, 45, 90 triangle. Okay. So you guys have to break out Pythagorean theorem. Right? But you know what? If you have a 45, 45, 90, okay, let's take that one of those real fast. Let me do real simple. Let's say this is like 1 meter and 1 meter, or maybe like 1 Newton and 1 Newton, right? If you like force vectors, which is like the theme of this chapter, right? Forces. Okay. Do you guys know what this number is exactly? It's like the square root of 2, which is approximately 1.414. Maybe a good fact to put in your back pocket. Right. You guys good? Did they just ask what exactly was the question? Magnitude and direction. Yeah, and direction. All right, so let's do bearing. Now, bearing is relative to a north-south line. So we're looking at this angle right here, right? Or for me, maybe this angle right here. I'll call this like beta. Right. Now, if you go east as much as you go south, then this is necessarily a what degree angle?
45?
Yeah, 45. That's 45 degrees, right? You can see that just by eyeballing it. Okay. But suppose you had like wacky numbers. How could you figure this out systematically? Theta is equal to what? Inverse tan of opposite over adjacent, right? Should be 45 degrees. Okay. And what about here? So that's your guys' triangle. Okay. What about my triangle up here? You can say beta is equal to inverse tan of opposite over adjacent. 60 on 80. The meters cancel. Okay. And I should get pretty close to like 37 degrees, I think. Maybe that's that number. So I've seen that so many times, right? 3, 4, 5 right triangle. Okay. Right, you guys good there? Okay. Everybody good on number 83? All right. So next up on the paper is up to 56. I know they're out of order a little bit. So 56. What is the meaning of a coefficient of friction that is greater than 1, and how would you measure that? Okay. So go back and remind you guys a little bit about coefficient of friction. I do have a friction lab lined up for you guys later this week, so pay close attention to this one just because this concept is definitely going to come back in the near future. So we do a real straightforward situation of, actually I can demo it right here at these materials within reach and distance. Okay, so object, force spring scale, okay, I can pull with some force and drag it across, right? Okay. Let me draw a free body diagram for exactly what you just saw. We got the floor, or I guess like this copy paper. Okay. We've got this 1 kilogram mass right here, got a little hook on it. Okay. And I take the spring scale and pull with the spring force to the right. Okay. Okay. And you guys saw that drag across it at constant velocity, which is a special situation because constant velocity is what's the acceleration of constant velocity? 0 meters per second squared, which means what's the net force? 0 newtons, right? You guys remember here that no, long weekend. You guys remember forces cause accelerations, right? What's the acceleration of an object? Well, it's the net force acting on some mass, right? That's our new way of thinking of acceleration, right? From a dynamics point of view, right? So if there's 0 acceleration, like 0 change of velocity, then there's 0 net force. So I'm about to draw this free body diagram, FBD, free body diagram for what you just saw. Okay, this right here. Let me get a force reading. I'm gonna get a reading on this. I'm looking at looks like about 3 newtons to pull at constant velocity. I'm looking at 3 newtons right here. 3 newtons of pulling force. Okay. Right. Oh, how much does 1 kilogram weigh in Earth's gravity? 1 kilogram weighs how much at surface Earth? 10 newtons about 10 newtons. Yeah, about 10 newtons. Okay, so I definitely have a weight of about 10 newtons, which means the normal force must be how much? Also 10 newtons, right? Okay. It's always the cosine component of the weight. In this case, 0 degrees because it's a horizontal surface. Cosine of 0 is 1, so like 100%. Okay, so 1 force down, 1%. Okay. Then I was pulling with 3 newtons of force, right? It's kind of proportional. So I'll say the force from the spring force was 3 newtons. But the fact that it was going across a constant velocity means my free body diagram is not finished. I also need a what force? Friction force. So F sub FR, friction force, okay, which also had to have been 3 newtons because it had to balance out the pulling force so that the net force was 0. Net force 0, 0 acceleration, constant velocity. Right? Is that okay? Okay. All right. So here's where remind you guys about coefficient of friction. Coefficient of friction. Okay. Now this is a material property. In this case, whatever this metal's made out of, and this paper, right? There's some material property that will establish the friction between those two. But there's a relationship between this friction force and this normal force. Okay. And it goes like this. The friction force is equal to coefficient of friction times the normal force. Okay. Actually, that's specifically true if we're talking about kinetic friction. Right. So if 2 surfaces are actually sliding past each other, right? Okay. See if it's static friction, this turns into an inequality because it's like you've got this object parked here, you put a little force, it doesn't move at all, and then you increase that force, and the friction automatically responds. Right, it builds up more, and it can go up to some point, and then finally the friction breaks. Okay, but here we go. So something like this, right? Now, see, here's what coefficient of friction is, right? Or I should say coefficient of kinetic friction if they're sliding past each other. Okay, so that one right there. Okay, now you can rearrange this to get coefficient of friction is equal to the ratio of friction force to normal force. Is that? So who can tell me for what I just did? Let's just demo this again. This right here. You're seeing it live action. Here's the animation. Okay. What is the coefficient of friction between this material and this material? Who sees it? 3/10. Yeah, 0.3. You guys see 3/10? That 3 divided by that 10. Right? Okay. I know that's 10 because that's 10. I know that's 3 because that's 3. Right, so that 3 over that 10, that's 0.3. Isn't there a coefficient of friction of 0.30? Is that right? Now that's a pretty common type coefficient of friction, like 0.3. Right. Now, you guys good so far? Okay. So with all that context, let's go back and look at this question again. What is the meaning of a coefficient of friction that is greater than 1.0? Whoa, greater than 1? Here, this is 0.3. What? Hey, what if? So suppose I replace this regular paper with like sandpaper, right? Maybe that'll do it. I don't know. Okay. So if the coefficient of friction between this material and sandpaper was like 1.1, what would that mean?
Friction is greater than normal force.
Yeah, this friction would be greater than the normal force. Huh. Okay. Do you guys think that ever happens? Could it ever happen that the friction force is greater than the normal force? Oh, wait a minute.
Glue.
Oh yeah, maybe glue. I guess that would maybe that technically somehow have to think on that
I
one.
don't think that's chemical property, not physical, but I'm not sure.
Yeah. You have me think on that. Here's one place I do remember seeing such a case was was taking some traffic courses back in college. You guys do like an engineering track, you might take a traffic course. And between those rubber or whatever they make tires out of in an asphalt road, if it's a case where you have new tires and the road is dry, so it hasn't been raining, you can get a coefficient of friction of like 1.1. Right? That can happen. Right now, if it's raining, that goes out the window. The coefficient of friction drops. Right, or if the tires are worn. Right, but yeah, if it's like brand new tires, brand new pavement, dry, blah blah, Yeah, it might be the case that the friction could actually be more than the normal force. If that were true, what would be easier? Would it be easier? Let's say there's a car that's just parked, right? You're just looking at this parked car. Would it be easier to lift the car or to push the car across the pavement?
Easier to lift.
It would actually be easier to lift it, wouldn't it? If it was a coefficient of friction greater than 1. Whoa, that'd be crazy, wouldn't it? Right? It'd be actually easier to lift the car, right, than to drag it. Right? So yeah, those are all implications embedded in having coefficient of friction greater than 1. Right? Again, that's a really rare thing to happen. You just saw in front of you right now a coefficient of friction of 0.3, right? But could happen, right? Right. Guys, good. Right. Number 90. If you use a horizontal force of so many newtons to slide this kilogram wooden crate across the floor at constant velocity, what is the coefficient of kinetic friction between the crate and the floor? Oh, we almost pretty much did that, didn't we? What we're looking at right there. So it's just kind of repeat that, but just make up new numbers. So floor, got a crate. Center of mass. Okay. I said constant velocity, which all the forces are going to balance. So let's throw some forces on. Switch color. Switch to burgundy color. All right. So I'm going to have a cart mass of let's say 14 kilograms. 14 kilogram mass. Okay. So how much does my cart weigh?
140.
140 newtons. Good call. So the weight is 140 newtons. Which means the normal force is how much? 140 newtons. All right. Okay. And then, what else I say? They did give you the drag force, right? So let's say I'm pulling with F sub pull as like 35 newtons, right? Now, if I just stopped there and walked away, would that cart be in that crate be in equilibrium? No, it'd be accelerating to the right. Right, so to put it in equilibrium, I definitely need a friction force, in this case of also 35 newtons. Right. Okay. So you guys took the mass, translated that into a weight, and said, well, the normal force must just be balancing the weight as long as it's a level surface and nothing crazy going on. Right. Also, you have to be pulling horizontally. See if I was pulling at some angle, do you think if I was pulling up a little bit, that would alleviate a bit of the normal force? Make this a little bit trickier problem to solve? Yeah. But as long as you're pulling horizontally, then the normal force can match the weight and everything's a lot simpler to solve, right? Right, so coefficient of friction, coefficient of kinetic friction. I've got say friction force compared to normal force. So I have 35 newtons friction force compared to 140 newtons of normal force. Yeah, there you go. Yeah. Okay. All right. You guys good? You know what? I'm pretty sure I told you guys last week, but see if you guys remember this or make sure I did. Coefficient of kinetic friction compared to coefficient of static friction. Okay. Which one of these? Static is bigger? Yeah. All right. Yeah. You guys remember this, right? So static is larger. Okay. Now we're talking about the same materials. So how about this crate let's suppose it starts just at rest, like it's genuinely like at rest relative to the floor, right? And you start pushing on it, trying to break the initial friction, right? Do you have to suppose you put 35 newtons of pushing or let's say pulling force, put a rope on this thing, you're pulling with 35 newtons, right? Is that crate going to move? Not yet, right? It might be pretty close. It might be like, maybe just need a little more force. You might need like 40 newtons or 45 newtons to break that initial friction. Okay. Now, once you break that initial friction, then you can decrease your pulling force down to 35 to match this 35 newtons of friction force. Right. But yeah, static friction is always going to be greater than kinetic friction for whatever the material is. Okay. You know what I want to do? I'm going to draw you guys an extra graph here. Gotta be careful when I tell different classes because okay, got 3 of the different levels of physics classes and sometimes lose track of like what I told what class, but here, tell you guys this anyway. Okay. So let's look at coefficient of friction, so mu, coefficient of friction, as a function of the speed between two surfaces. Okay, the speed could be in meters per second. Coefficient of friction, that's like Newton per Newton, which is like a unitless ratio, right? Okay. Now, if the speed is 0, say that crate was not moving relative to the floor, then there's going to be like some coefficient of friction, and that represents the coefficient of static friction, right? Which, remember, this is friction force compared to the normal force, right? Newton per Newton, or just unitless ratio, Newton per Newton, right? Right. Now you break the initial friction and you start sliding, right? And you know what? Maybe you slide faster, faster, faster. Maybe try multiple speeds, right? So how about the speed between the two surfaces is like 5 meters per second. Then you bump up to 10 meters per second, and then 15, and then 20. Like you're trying all these different speeds with meters per second, right? Right. And then what you'll see, I mean, this is an experiment, so I'm just telling you guys the results, okay, is that this coefficient of kinetic friction stays pretty much the same all the way across. It's like a horizontal line. Okay. So once you break the initial friction, like that coefficient of friction will just jump down. Okay. And this right here is coefficient of kinetic friction. Okay. Guys up there? All right. Yeah, there's definitely a problem I want to do with you guys that involves a car braking to a stop. Actually, I think that might be here, I'll throw it in right here. Okay, let's go off script a little bit. We're gonna do one that's not from that page unless I'm missing it. Okay. We're gonna do a car braking to a stop. Okay. Car brakes
94.
to, oh yeah, is that on there?
Yep.
Oh yeah. Let's see what exactly to say. Driving a car at constant speed on the road, car turns red, slam on the brakes. Oh, okay. Yeah, that definitely is that scenario. Now I'm gonna go a little bit a different direction with this. Car brakes to a stop. Okay, so we'll do the setup that will actually probably also be a good start for that same question. But then gonna go a little different direction with this. And so got ourselves a car. Okay, let's just have a horizontal road. It's pretty straightforward. Okay. Give this a rightward velocity, some like v naught, some initial velocity. So moving on to the right, getting things center of mass. Right. All right. Actually, tell you what the question is. Right. Here's the question. Here's where I'm going with this. If you triple the mass of the car, then what happens to braking distance? Okay, what's brake distance? Okay, so I don't know. You guys might remember from going back a little bit from kinematic motion. You guys remember if you triple the speed of the car? Guys, what's a factor of 3 squared? 9, right? And then, or I should do this factor 9 because final velocity would be 0 if it's braking, right? And then let's see, the friction wouldn't be any different, so acceleration doesn't change. The rate the car can slow down. So doesn't that factor 9 all get routed into the distance? Okay, you guys remember that? Okay, so if you triple the speed of the car, you actually need 9 times the braking distance. Okay, if you double the speed of the car, you're gonna need 4 times the braking distance. Guys know that? Right. Now that's different. That's not exactly what we're doing here. Here I'm changing the mass. Okay. I'm tripling the mass of the car. Okay. So what's that going to do to braking distance? Now, this right here is a really classic physics question. If you guys take physics in college, you're almost certainly going to see this question again. And there's a really funny counterintuitive answer to this. So here, let's go to this. Well, I need a free body diagram. So let's throw some force vectors on this guy. This guy has a weight acting down, mg. This guy has a normal force acting up, F sub n, which is as long as it's a level road and there's nothing crazy going on, it would also be equivalent to the weight, wouldn't it? Okay, so hold on to that idea. That's about to be important. Okay. And then if this car is braking to a stop, which way should I draw the friction force? To the left, right? Because he's moving to the right, so he's braking, the net force must be to the left, right? So I'll do F sub FR, just like that. There you go. There's my free body diagram for a car braking to a stop. Is that okay? Right? Three forces: weight, normal force are balancing each other out. Right, and then the friction force is acting as the net force. Okay, braking to a stop. All right, so let's kick over to Newton's second law of motion. You guys remember it goes like this. Okay. So here, two different versions of it. Maybe I'll just do this version. Net force causes the mass to accelerate. In this case, accelerate, you might say like decelerate, like the car's going to slow down, but the magnitude of acceleration, right? So net force is equal to mass times acceleration. Okay, so that's all good. Okay. Hey, what is the net force on this car? Just the friction force, isn't it? Because the two verticals cancel out, and that just leaves the friction force. So this net force is provided by the friction. Friction force is the net force. Mass times acceleration. Is that okay? Okay. But you know what? From a few minutes ago, this is why I'm doing this one right now. You guys remember this one right here? Friction force is coefficient of friction times the normal force. Okay, so we can get a bit more specific and say that this friction force is the same thing as the coefficient of friction between the tires on the road times the normal force. Right? I'm simplifying a little bit, maybe coefficient of kinetic friction or static that goes up to some point. Right, so simplifying a little bit, but you guys get the idea, right? Right. And hey, the normal force, well, we said that would just be equivalent to the weight, right? As long as the road's level and those are the only two vertical forces, right? That has to be true. Car's not accelerating up and down. So this is just mg, isn't it? So coefficient of friction times, well, what's equivalent to the weight, that's going to be mass times acceleration of the car. Guys so far? Okay. Now here's where something funny happens. What cancels out on both sides? Mass of the car. Okay. I'm going to swap both sides while I'm at it to tell you something about the car slowing down. And that's just going to be coefficient of friction times the gravity field of the planet. All right. Is that
Nothing happens to breaking distance.
boom? There you go. Yeah. You guys hear what Steven's saying? Is that here, if the if you triple the mass of the car, right? The fact that mass canceled out, right? It's gonna have no effect, right? So if you have like a light car and like a heavy truck, side by side, and you start out, same road, same tires, same everything, except just different masses, right? One's like 3 times as massive, right? And they're going at the same speed, and they slam on the brakes at the same time. Do they have the same stopping distance? Yeah, according to this, they do, right? Right. Now, yeah. In real life, is that is that an approximation that's not 100% true? Maybe you could make a case, but yeah, again, this is like a classic physics question. If you see that in college, that's the answer. Exactly. All right, guys, good there. All right, let's flip back over to your book questions. Number 91. A crate that many kilograms is pushed horizontally with a force of that many newtons. Oh, and they told you what the coefficient of friction is. So find the acceleration of the crate. All right, we do that. Number 91. I'm going to change the numbers for the notes just so you get a little bit more independent practice, but the same premise. All right, we got ourselves a crate. There we go. I'm going to say that the mass of my crate is, I'll call it 150 kilograms. Right, you guys have something different. And I'm gonna call the coefficient of friction between the crate and the floor as like 0.25. How about that? Okay. And I'll push with the force that I'll label on the free body diagram. So free body diagram. Okay, here we go. Okay. So this crate is gonna have a weight and a normal force that's gonna balance each other out. Okay. I'm pushing with some force, F sub push, okay, and there's going to be some friction going on, F sub F bar, right? Now, from the diagram, so do you guys see that this cart is, this crate is not going to be in equilibrium, right? There's going to be a net force on this crate, is that? Okay, all right, so we got next here. I need some numbers. What's the weight of my crate? You guys think 1500 newtons? Right? You guys see where I got that, right? Mass times gravity. Here. So here, 150 kilograms times about 10 meters per second squared, give about that many newtons of weight. Okay. So wouldn't the normal force also be that many newtons? Right? I need to give you guys a pushing force here. Let's say I have a pushing force of 400 newtons, 400 Newton pushing force. Okay. Wonder what is the acceleration of that crate? Okay. Well, before I can figure that out, you need to figure out what the friction force is. And I know that friction force, seen this at least a couple of times today, is equal to coefficient of friction times the normal force. Right? So wouldn't that be let me pause this recording here. All right, recording is resumed. So we got 0.25 coefficient of friction and a normal force of 1500 newtons. Right. Yeah. All right, so that looks like 375 newtons of friction force that I have. I can take that. Oh. Right there. There's equals 375 newtons. Okay. Remember, I got that from knowing what the coefficient of friction is and also the normal force, which of course is balancing the weight. Guys good so far? Okay. Let's kick over to Newton's second law of motion. The acceleration is equal to the net force acting on some mass. Right? Oh, yeah.
The last round, where did you put 1500?
This 1500? Because I know the mass of the crate. I just made up the mass of the crate, but you guys have different mass. And isn't weight just mass times gravity field? Right? So if I take 150 times 10, I get 1500. Yeah. Right. Yeah. So to go from mass to weight is pretty straightforward in the metric system. You can just multiply by 10 meters per second squared, right? Okay. So acceleration is now net force. Well, the verticals I can ignore because they just balance out anyway. But look at the horizontals. I'm pushing with this much force, and there's this much friction. Right? So shouldn't it be this many newtons minus this many newtons for the net force? There's my net force. Okay. Acting on this many kilograms worth of mass. Right? Okay, you guys good? So acceleration is, let's see, this many, yeah, that was right. That many kilograms, sorry, that many newtons acting on this many kilograms. Righto, about 1/6, so that's what, point, something like that. Meters per second squared. All right. Hey, would it be possible for the friction force to be greater than the pushing force? That could happen, right? And if that were the case, then what would the crate be doing? Slow down. Ah, yeah. If you're not pushing hard enough to okay, yeah. So if the friction force is greater than the pushing force, then the crate would be slowed down, wouldn't it? Guys, good? Okay. Now, that one's a little complex, so while you guys are digesting that, maybe walk through this again. Okay. So they told you three things. They told you the mass of the cart, the coefficient of friction between the cart and the surface, and also the pushing force. So those are like three given values. Boom, boom, boom. Okay. And they said, what's the acceleration of the crate? Okay. And okay, so this was a process. You have to draw a free body diagram, say, well, the weight and the normal force are balancing out. So I have numbers for each of those. Okay. In fact, the weight is to do mass times gravity field, right? So you guys can do that. So boom, boom. Now you know the weight and the normal force. Okay. But you still need the friction force. You can go through coefficient of friction to get the friction force. Right? It's just coefficient of friction times the normal. And remember, the normal had to be balancing out the weight. So you know all these magnitudes. So pop it all in. You can get the magnitude of the friction force. Right? Then you say, well, if you're pushing horizontally with some force, and by this point you know what the friction force is, if you take the difference between those, that will give you the net force. And then that net force acting on the mass of the crate tells you the crate's acceleration. Boom, boom, just like that. Okay. Guess that. All right. So it looks like just one last main question I had assigned here. So let's definitely do this one. Advertising. Joe wishes to hang a sign weighing this many newtons. Oh, hey, let me pause right here. Look how they typed this. 7.5 times 10 to the 2 newtons. That's scientific notation, isn't it? What's a more colloquial way to say that number? Oh, careful. Yeah. So 750, right? Yeah, you guys see 750? Right, so 2 decimal places, right? So 750 newtons, right? Now, there is an advantage to writing this in scientific notation. It's kind of a technical thing, but see that 0 right there? See if you write it with scientific notation the way you did it, then that 0 actually is significant, right? The fact that they took time to type that 0, that is a significant number. But if they wrote out the number, like, if they wrote out the number 750, it'd be ambiguous as to whether that last 0 was significant or not. Is it really 750? Is it 753? Yeah, right. Okay, but we know it is 750 exactly. Okay. All right, so it makes this 30-degree angle to the vertical, just like they show in this diagram. And cable B is horizontal. What is the tension in cable B? What is the tension? So what we're going to do is find this point right here where everything comes together. Each of the cables and the sign hanging down doesn't all connect right here at this point. We're going to do a free body diagram from that point where all 3 cables come together. The sign hanging down and the rope pulling up to the left and then the cable to the right. Okay. To do a free body diagram. Okay. We're going to introduce a Cartesian system that runs parallel perpendicular to gravity. Because at some point we're going to have to break out trigonometry, SOHCAHTOA, do some sine, cosine, get some vector components. Okay, so I got my Cartesian system set up. Okay. Let's look at the 3 forces. I got the weight of the sign acting down. So for now, I'll label that mg, but I'll go back and put in a number later. Okay. There's some cable pulling up and to the left. I'll call this T sub A, the tension in cable A. Okay. And then there's going to be a tension in cable B pulling to the right. T sub B, tension in cable B. Okay. Is that okay? Free body diagram. Okay, all good? They gave you 2 things. They gave you the weight of sign and an angle. All right, so I'm gonna, I'll make my angle 30 degrees also, just like you guys have 30 degrees to the vertical. So I'll do this too. Okay. But I'm gonna make the weight of my sign, say 800 newtons. 800 newtons. Okay. All good. Okay. Now, if that sign's just hanging out at rest, then isn't it true it would be equilibrium in a state of equilibrium? And equilibrium is going to have these conditions. The sum of the forces in the x direction is 0 newtons. and the sum of the forces in the y direction is also 0 newtons, right? There's my condition for equilibrium. Okay. Now, two of those forces are already aligned to my coordinate system, right? The weight of the sign and this tension B that we're ultimately solving for. Okay. But what about tension A? Ooh, don't I have to break this into components? Okay. Now you could go up, over, or over, up. It doesn't matter which way you do it. Maybe I'll do up, over. I don't know. Why not? Okay. So that cable A is partly pulling up and partly pulling to the left. Okay, partly up, partly to the left. Is that true? Is that? Hey, do you guys think that this up has to match this down? And you guys think that this left has to match this right? I think so. I think so. Okay. So if that's true, then I could say here is here, let's do this. Is this component right here going to be equal to tension A times cosine of 30 degrees? Is that true? Right? And that must be equal to 800 newtons to satisfy this condition right here. Right? So this minus that is equal to 0. Okay. So I guess properly I could say this. Tension A times cosine of 30 degrees minus 800 newtons is equal to 0 newtons, right? Or you could just say tension A cosine of 30 degrees is equal to 800 newtons. Right, that right? Okay. Oh, now we can solve for tension A, can't we? Great. Is that? So shouldn't tension A just be the weight of the sign divided by cosine of the angle? Right? Actually, before I start plugging and chugging, just eyeballing my free body diagram, is what's a larger value? Tension A or the weight of the sign? What's going to be a bigger number? Yeah, tension A has to be, because this is the hypotenuse of a right triangle where one of the legs matches the magnitude of the weight of the sign. So it has to be bigger. Okay. See, that's true. What's 800 divided by cosine of 30 degrees? Well, cosine of 30 degrees is something between 0 and 1. Okay. It's like what, 0.86 something? Yeah, look at that, look at that. Tension of cable A is like this many newtons. 3 sig figs, like that. Right. Now, is tension B going to be equal to tension A times sine of 30 degrees? You guys see that? You guys see this is equal to this? So tension B must be tension A times sine of 30 degrees. We figure out what tension A is. I meant to say, I know I'm running out of paper here, but that satisfies this top condition here. Some of the forces in the X goes to 0, right? So this and this have to balance out. Therefore, they have to be the same. That's why I skipped a step. I should have said TB minus TA sine 30 is equal to 0, but right. So what is that number times sine of 30 degrees? By the way, you guys remember what is sine of 30 degrees? Just all by itself. 0.5, yeah, 1/2, right? Right. So that's a good one to know. Okay. Here we go. Tension to cable B, which was the question all along. I'm getting this many newtons. Of course, this is just my made up numbers for the notes. You guys have different set of numbers from the book. But it's the same process, right? You guys see that? In fact, I think I can go from the setup to the answer in all one step. Okay, once you see the big picture. Okay. Oh, because the fact that this weight is equal to this component of tension A, and this tension B is equal to this component of tension A, right? Isn't there just a relationship between the two legs of a right triangle that's called tangent? You guys remember tangent of 30 degrees? Hey, wouldn't tangent of 30 degrees just be this divided by this? Right? So I can solve this even faster than we did this way. I'll do a little step over here. I'll solve this a separate second way. So tangent of 30 degrees must be equal to tension B, because this is tension B, it's the same thing. Right? Tension B, same magnitude, I should say, divided by the weight. Right? cross multiply the weight. So can I take 800 newtons, multiply by tangent of 30 degrees? And that would tell me what tension B is. It's an alternate way to get there, right? I bet if I do that, I'll also get 462 newtons. Let's see if I do. What is 800 and 30 degrees? All right, we got a lot of physics and trigonometry relying on this right here. So this better come out to 462. I better see a 462 on my screen. Hey, it is 462. Oh yeah, it's the same thing. Look at that. Right, there you go. There's one way to solve it. Good. And here's a faster way to solve it. Two different ways to solve it, right there. All right. Oh, that takes me exactly to the end of class, so that worked out perfect. You guys got any questions? All right, that is a wrap.